So there is this, I think, sense from what I'm hearing in your story of being able to kind of scratch that itch as a polymath and be able to see how these different domains of engineering and biology are intersecting. Then there's the reality of actually doing, the academic work, seeing the state of neural networks back, in the day when we had access to, I imagine, a lot less compute and data. What did the reality of it feel like once you got into it?
Yeah, I mean, exactly what you said. I think ultimately, we went through and what we call an AI winter, right? I'd learned and used neural networks in some of my research, but once I arrived at Princeton for grad school, folks had kind of moved on to, what was understood to be, a better approach to machine learning at the time, statistical learning, Bayesian models, things like that I retrained in basically as a graduate student. And again, Princeton was an amazing place, very strong computer science program that allowed us to kind of capture all of that knowledge. But at the same time, I did have the background that when kind of this modern AI took off again to really jump on board again very, very quickly. But the reality is that I actually gave an academic talk about kind of the idea of AI, modern AI, and why I think this time it is different. To be honest, we have gone along for the ride for decades around like the promise of AI. And you gave some examples of why AI is interesting today and all these capabilities, but I think what gets me excited about AI as someone who does kind of basic science, especially in biology, it is the idea of foundation modeling. It's the idea that you can have models instead of having very specialized models for specific tasks, right? So in biology, what was that? Like, you need really to have large models, you need a ton of data. And in biology, the type of data that you have is kind of, X-ray images, scans, things like that, or like pathology slides. So these are the things that like we started with early on. And then a few applications here and there. But beyond that, science is data starved. Right? So we do not have the kind of scope of data that you need to train really large models to really take advantage of the emergent properties that these larger models really have. The promise of modern AI and specifically foundation modeling is this idea that you can build really large models on relatively cheap, kind of self-supervised data that forms a foundation for going into areas that are much more data starved and with a lot less data, be able to fine-tune that model for a specific task, but now in a much, much smaller regime in terms of data set sizes that you need. Again, the idea being that these foundation models have pre-learned a lot of biology on their own by just interacting with large swaths of data, and so they have a much easier time getting to an answer as opposed to kind of starting with a very large model for a small data set that will never work. So I think that is fundamentally why I think this time is different from like other approaches to AI, because we have come to realize that instead of having different models for different tasks, we can have foundation models that then we can kind of retrain and gear towards different applications, including biology.